You think you know why it's so hard to track a hypersonic missile. You figure it's the speed too fast. Radar can't keep up. It's all about reflexes. But it's not. There's something happening with these missiles that goes way beyond pure speed. Something that makes the tracking problem fundamentally different. Different from tracking anything else that's ever flown. And here's the surprise. It's not secret technology. Not a special coating. Not some classified breakthrough from a superpowers lab. It's physics. Pure physics. Physics that had already been completely explained long before the first operational hypersonic missile even existed. In 1961, a man named Richard Feynman was sitting in a classroom at Caltech, the California Institute of Technology, delivering one of the most famous lecture series in the history of science. He's explaining how light interacts with matter, how photons behave when they hit free electrons, what happens to electromagnetic waves in an ionized medium. Feynman wasn't thinking about missiles. He was thinking about the fundamental nature of the universe. And without knowing it, he described with absolute precision the hardest air defense problem of the 21st century. What he explained in those lectures is exactly the mechanism that makes modern hypersonic missiles, the Russian Avangard, the Chinese DF-17, the American programs currently in development essentially invisible to conventional radar. The word invisible here is precise and deserves our attention before we move on. We're not talking about optical invisibility. You can see a hypersonic missile in the sky if you're in the right spot. What we are talking about is radar invisibility. The inability of defense systems to detect, track, and intercept these projectiles using the electromagnetic waves that every radar system in the world uses to monitor airspace. And the reason for this invisibility isn't found in engineering labs. It's in the laws that govern how the universe works. In this video, you're going to understand the real mechanism, the physics that no engineer designed and that no military budget can ever change. Let's start by fixing something almost everyone gets wrong about hypersonic missiles. What makes them fundamentally different from anything else that flies fast? The Mach number measures speed relative to the speed of sound. Mach 1 is the speed of sound, about 340 meters per second at sea level, or just over 1,200 kilometers per hour. Mach 5 is 5 times that, somewhere around 6,125 kilometers per hour. The threshold between supersonic and hypersonic is Mach 5. But this isn't just a number, it marks a qualitative shift in how air behaves around a vehicle. Below Mach 5, we've learned to solve the engineering challenges since we broke the sound barrier in 1947. Above Mach 5? Different regime entirely. The same engineering solutions stop working. Here's how it works. When an object moves through air, the air has to get out of the way. At subsonic and supersonic speeds, sound travels ahead like a messenger. The air gets warning and parts before impact. Above Mach 5, that doesn't work anymore. The object's moving so fast, the air can't get out of the way in time. There's no warning. Instead, the air compresses violently, forming what physicists call a shock wave. A wall of compressed air that slams right in front of the vehicle like a shield of extreme pressure. This is where intuition fails. You probably think extreme heat comes from friction, the vehicle rubbing against air like your hands heating up. But no. Friction's there, but compression's the real culprit. When air is compressed so violently and so rapidly, the kinetic energy of the flow is converted into thermal energy. It's the exact same basic principle as a manual air pump that gets hot when you push the piston down hard, but on a radically more intense scale, applied to a column of air that has nowhere to go. In the shock layer surrounding a hypersonic vehicle, temperatures hit over 10,000 degrees Celsius. The sun's surface, about 5,500 degrees. We're talking hotter than our nearest star. This isn't a design flaw engineers can fix. It's thermodynamics. Kinetic energy has to go somewhere. When air can't escape, it becomes heat. This extreme heat, that's the first piece of the puzzle. But on its own, extreme heat would just be a materials engineering problem. What turns extreme heat into a fundamental physics problem is what that heat does to the air around the vehicle. Because at 10,000 degrees Celsius, air is no longer air. You probably learned in school that there are three states of matter: solid, liquid, and gas. But there's a fourth state, far and away. It's the most abundant in the visible universe. The sun's made of it, the stars are made of it, and over 99% of all visible matter exists in this state. Plasma. Plasma isn't just hot gas. It's gas that's undergone a fundamental transformation. Electrons have been stripped from their atoms. Normally, nitrogen and oxygen atoms have electrons tightly bound in orbits around the nucleus. Electrical attraction keeps them together. But heat gas to extreme enough temperatures, the temperatures around a hypersonic vehicle, and electrons gain enough energy to break free. Atoms lose electrons and become positive ions. Electrons move independently. You get a gas of charged particles, positive ions, and free electrons without ordinary gas's neutral structure. That's plasma. Plasma behaves completely differently around electromagnetic fields than neutral gas does. Neutral gas has no free charges to respond. Plasma does. And that's what changes everything. Around a hypersonic vehicle, shock layer temperatures ionize the air, not all of it, but enough for a continuous plasma layer. Scientists call it a plasma sheath. It wraps the missile like a second skin, physically cutting it off from external electromagnetic signals. Now you might be thinking, that's theoretical. Is there real evidence? There is, and you've probably heard of it. In July 1969, Apollo 11 was returning from the moon. As the command module entered the Earth's atmosphere at high speed, the astronauts and NASA completely lost radio contact. For roughly 4 minutes, no transmission went in or out of the capsule. The engineers at Mission Control in Houston heard only static. It wasn't an equipment failure. It wasn't interference. It was plasma. During re-entry, the Apollo capsule reached speeds of roughly Mach 32.6 times the hypersonic threshold. The temperatures around the capsule were so extreme that the air completely ionized, forming a plasma sheath that blocked all radio communication. 4 minutes of complete silence. 4 minutes where NASA engineers had absolutely no idea what was happening to their astronauts. The same phenomenon occurred on all Apollo missions, and on the space shuttle. On every re-entry capsule NASA ever operated. Engineers expected it, planned for it, and knew exactly when it would happen and when it would end. This isn't a hypothesis. It's not a lab simulation. It is a documented physical effect, accurately studied and understood one that NASA repeatedly recorded with real equipment, on real missions, with real astronauts who desperately needed to communicate with the ground. The plasma sheath exists. The question now is, how exactly does it interact with radar waves? To answer this precisely, we need to turn to the man who spent decades mapping exactly this type of interaction, and the answer comes from a place that no one who designed these missiles ever expected to find. Richard Feynman was born in 1918 in Queens, New York. He won the Nobel Prize in Physics in 1965, shared with Julian Schwinger and Shinichiro Tominaga. He was famous for physics, sure, but especially for explaining it with radical clarity. The legend goes, if Feynman couldn't explain something simply, it meant he didn't fully understand it. But what matters isn't his personality, it's what he built. Quantum electrodynamics. QED. QED describes how light interacts with matter at the quantum level, how photons, particles of light, electromagnetic radiation, radar waves behave when they hit electrons, how electromagnetic energy gets absorbed, emitted, and reflected. QED is the most accurate physical theory ever developed, verified to parts per billion precision. When lab measurements match theory that exactly, you stop calling it theory and start calling it reality. QED explains why metal shines, why glass is transparent, why light speeds up or slows down changing mediums. Modern electromagnetism stands on it. Feynman developed path integrals, a counterintuitive but powerful mathematical approach. The idea: a photon doesn't take one definite path between 2 points. At the quantum level, it explores all possible paths simultaneously. The probability of reaching its destination depends on all these paths summed together, deeply influenced by whatever medium it's traveling through. When the medium's packed with free electrons like plasma, this interaction becomes critical. Free electrons aren't passive around electromagnetic waves. An electromagnetic wave passes through free electrons and they respond to its electric field. They move. They oscillate. They create their own electromagnetic radiation, interfering with the original. Billions of electrons oscillating together to a radio wave that's called plasma oscillation, and it has a specific natural frequency determined by electron density. More electrons, higher frequency. Physicists call this the plasma frequency. And here's the question that changes everything. What happens when a radar pulse hits plasma with a different natural frequency than the radar? In the Feynman lectures on physics given at Caltech, 1961-1963, one of science's most important texts, Feynman maps exactly this: how electromagnetic waves interact with free electron mediums, reflection conditions, absorption conditions, how plasma frequency acts as a threshold separating completely different behaviors. In 1961, the world's most advanced hypersonic missile didn't exist, but the physics governing its invisibility, already completely mapped. This is QED's beauty. It doesn't describe specific technologies. It describes how the universe works. Build an object operating under sufficiently extreme conditions, and the universe applies its rules with all the precision QED predicts. The plasma frequency is the exact parameter that determines what happens when radar waves try to pierce through the plasma sheath surrounding a hypersonic vehicle. How radar works, let's be precise. Imagine you're an air defense operator. Alert: hypersonic object approaching. Switch on the radar, send the pulse, wait for the echo. What do you get? A radar emits a pulse of radio waves in one direction. They travel, hit an object, bounce back. You detect the echo. Travel time and direction tell you where it is. Simple system. Works perfectly for airplanes, ships, vehicles, anything reflecting radio waves. Now, what happens when radio waves hit the plasma sheath around a hypersonic vehicle? Everything depends on one parameter: radar frequency versus plasma frequency. Radar frequency lower than plasma frequency. The subplasma regime, the wave reflects, bounces off the plasma sheath. An untrained operator sees a return, promising. But here's what actually happened. The wave bounced off the sheath, not the missile. Radar detects the sheath as a reflector, not the object inside. Depending on flight conditions and sheath geometry, you get confusing, incomplete, or useless reflection data. The missile hides behind the sheath. What about higher frequencies, above the plasma frequency? The wave penetrates the sheath. Plasma doesn't reflect it. But plasma isn't transparent. It absorbs energy. Free electrons oscillate in response to the wave, transferring energy through collisions with ions. The signal fades as it penetrates deeper. Dense enough sheath, and the signal dies before hitting the missile. Even if a fraction bounces back, it crosses the sheath again, getting absorbed again. Any survivor falls below detectable noise. Here's another problem with higher frequencies: shorter range and more atmospheric absorption. Using high-frequency radar to punch through the sheath means losing operational range right when you need it most, because hypersonic missiles travel hundreds of miles in minutes. The symmetry's elegantly cruel. Low frequencies reflect off the sheath without hitting the target. High frequencies get absorbed before arrival or on return. Either way, reflection or absorption, the result's identical. Nothing detected. Plasma has two ways to stop radar waves. Both cover every scenario. Feynman described this exactly. Path integral mathematics and QED structure precisely predict this frequency threshold, reflection regime, absorption regime, not academic curiosity, but direct consequence of photon-electron equations. This changes everything. It's not primarily an engineering issue. You can't solve it with more powerful radar or transmission power. You're facing a fundamental property of ionized matter. The plasma sheath exists as long as the missile flies hypersonic. The plasma frequency defines what can and can't pass through. Physics doesn't negotiate with defense budgets. Radar invisibility is not an engineering achievement. It's an inevitable physical consequence of flying hypersonic in the atmosphere. But here's a detail most people miss about hypersonic missiles. The plasma sheath doesn't just block the enemy. The radar problem, incoming waves can't penetrate to detect the missile. But the sheath works both ways. Any signal leaving the missile radio transmission, data links, GPS faces the same physical wall. During maximum speed, the missile's completely isolated from its operators. GPS signals can't penetrate. Outbound data links can't pass through. It's flying blind and silent, no external information, can't transmit position or status. This happened with Apollo. The capsule couldn't reach Houston. Houston couldn't reach the capsule. Not static. It was that no signal, either direction, could cross the plasma sheath. For a manned re-entry vehicle, this is manageable. Astronauts knew what was happening, knew the blackout lasted minutes, and waited for the capsule to slow down. For a hypersonic attack missile, it's complicated. These vehicles need real-time guidance, adjust trajectories based on target data, get position updates, communicate with operators who might modify or abort during flight. At peak hypersonic speeds, none of this works normally. Engineers developed partial solutions. Pre-programmed trajectory, load all data before launch, execute autonomously, no real-time communication. Another approach, physical design find regions where the plasma sheath is less dense, position antennas in those windows for limited transmission. But those are workarounds, not solutions. Maintain hypersonic speed and the sheath stays. It blocks most communications. Result? The same physics making the missile invisible also disconnects it from its operators. The most advanced object a world power can launch, traveling at speeds no defense can match, is simultaneously blind and mute during its most critical phase. Physics makes these missiles invisible to radar. Any way to detect them? Yes. But each approach has fundamental physical limits. None cleanly solves it. Most promising? Most ironic. Remember, the plasma sheath exists because shock layer temperatures hit 10,000 degrees Celsius. An object that hot isn't just warm. It emits intense electromagnetic radiation at that temperature, primarily infrared, but across multiple spectrums. The plasma sheath making the missile invisible to radar makes it shine like a star in infrared. Passive infrared detector sensors that only receive radiation detect the thermal signature from considerable distances. Satellites use similar methods to detect ballistic missile launches by engine heat. But infrared has its own physical limits. It tells you something's there and rough direction. Converting that to interceptor-grade coordinates is much harder. The infrared signature varies with viewing angle, altitude, flight phase. Orbital sensors have fixed geometry. See the object from one angle for one window, and fusing multiple satellite data for precise tracking is technically tough. There's also over-the-horizon radar, lower frequencies than conventional defense radar. Ironically, frequencies below plasma frequency reflect off the sheath, creating a detectable signature, but resolution's coarse. Detecting a disturbance isn't precise tracking data for interception. A multi-capable space senses infrared, synthetic aperture radar, electromagnetic disturbance offer potential. But that needs massive space infrastructure, real-time data fusion, and still hits physical limits of each sensor. The fundamental asymmetry. The hypersonic vehicle automatically benefits from physics. No engineer-designed radar invisibility. It emerges from nature's laws at sufficient speed. Defense has to build elaborate systems around those same laws, and everything hits its own limits from the same physics creating the problem. No computing power or engineering can change the fact that plasma at certain densities has a specific plasma frequency defining what passes through. It's not a technical vulnerability. It's the universe being the universe. We've come full circle. A physicist at Caltech in 1961, lecturing on photons and free electrons, not thinking weapons, not thinking air defense, thinking fundamental reality. Feynman said it. Nature uses only the longest threads to weave her patterns, so each small piece of her fabric reveals the entire tapestry. Same physics, same electrons responding to the same electromagnetic field, why mirrors reflect light, why metal shines, why plasma blocks radar. Single underlying pattern in situations Feynman never imagined together. The hypersonic missile isn't an engineering triumph over physics. It's physics expressing itself. Radar invisibility wasn't designed. It was discovered an inevitable property emerging from laws Feynman mapped decades earlier, without imagining it had become militarily urgent. Push technology far enough, you stop facing engineering problems and start facing the universe directly. The universe, as Feynman knew, doesn't negotiate. If this connection fascinates you, 1961 physics, explaining what's happening in military labs today. There's much more on this channel. The next video continues in this direction.